Hello, this is Marvin Glotfelty, and I'm a hydrogeologist and well driller from Arizona, here to give you another industry-connected video from the National Groundwater Association. Today, I want to talk about well siting, locating wells. Sometimes we might have a small, residential yard we're going to drill in. That's more of a question of how far from the septic tank we need to be and where it's going to be logistically convenient. So something like that is a scenario where there's not a huge amount of consideration required. But in many other cases, we might have many acres, even in some cases square miles, where we can select a better or worse site for industry, agriculture, municipalities, etc. So in those cases, let's talk for a minute about how we can go through that process. So let me share my screen here and show you some slides on this. So here's a Google Earth image. Now this is representing a fractured rock aquifer. So we have two general categories of aquifers, of course, fractured rock aquifers. This would be a sandstone. This is probably in southern Utah somewhere. And so in this case, the groundwater resides and moves primarily through these fractures in rock. And we're looking at an aerial view where you can see them in this rock outcrop here, also up here. And we see almost a checkerboard looking lines in this land surface, as well as some nice right angle turns to this stream moving through here. Those are indicative of these fractures. A stream is going to have a dendritic pattern if you leave it alone, like the branches on a tree. So it's not going to have these square right angle turns like this unless there's some kind of geologic structure that makes that happen. And that's what we have in this case. So in a case like this, we can do things without sophisticated approaches. And it's not to say that sophisticated approaches should be ignored. It's just that we can start with something like this. So by sophisticated approaches, I'm talking about satellite imagery, LiDAR, GPS type based imagery, and geophysical surveys. There's many different approaches that are all very beneficial for siting wells. There's ground penetrating radar. There's seismic surveys. There's gravity surveys, controlled source audiomagnetotellurics, many different ways to look at the subsurface, and they're all beneficial. We also can implement exploratory boring programs and learn a lot about wells. But let's just talk about, some simple things that anybody can do. So first, we look at just a Google Earth image, and we can site a well just based on something like this. So we first recognize that these fractures that we see at the land surface, they'll cross different formation boundaries, as you see in this left-hand image here. They can propagate just the way a pothole propagates through the asphalt. Even after it's been patched, they propagate to the land surface where we can see them, so we can know where the fractures are in the subsurface when they're vertically oriented like this. So we can then pick our area of interest, and that's a good first step. A lot of people skip over that, but we don't want to find great well sites that are not in the area where our client has the land. We have to go to the area where we're going to drill. Then we identify the fractures, and I've drawn a few of them on this image. They're not every one of them, but they're an example of what we look at. We can just draw a line where we see it on the image. And so where we have a geologic lineament, as we call them, that's at the land surface, that's going to represent a fracture that extends down to the water table. So once we've identified these, we go out to the field and we make sure that we haven't found a bunch of fence lines or game trails or non-geologic features. And when we know that they're real geologic features, so in this example within our area here, we have a number of places where there's two or more fractures that intersect. And at those places, that's where it would be a good spot to drill a well. If we go to those, we're going to encounter more groundwater and produce it in a more efficient manner. Now, where I'm showing you here, and in a lot of the area where I work, many of these fractures are pretty close to vertical, but that's not the case everywhere. So we also have to consider that. So let's say we have a scenario like this, where we've set up along one of these geologic lineaments here, and we see it shown by the slope surface here, but it's not that vertical. So if we drill straight down to the water table, there's the water table down at some depth, we drill straight down from where this rig is, we're going to hit the water table, but we won't have the fracture there, so the water won't flow to our well as readily. Well, we can do some real simple math and address this issue. So if we've got a triangle here, and that triangle, like any right triangle, a right triangle is the one where it's got a 90-degree angle, and that's why we're talking about here. It's straight down, so it's turning 90 degrees. This is a right triangle, and it's got three sides: the adjacent, opposite, and hypotenuse is what we call them. So if we take that adjacent side and we multiply it by the tangent of this angle that we can measure. So let's say we measure it 5 degrees or 2 degrees or 1 degree, just a little bit. We can determine this opposite length. And this opposite length down here, it's the same length that we need to move our drilling rig to hit the water and the fracture. So let's look at an example. Let's say that we have a 2-degree dip, just 2 degrees to our angle, and we're going to drill to 1,000 feet. So 1,000 feet, and the tangent of 2 degrees, if you do it on a calculator, is like 0.035 or 0.35. So that means 35 feet is how far we need to move over. Not that far, but if you don't move over, then you miss the fracture and you won't get the same water quantity. So this is the kind of thing, simple, common sense, anybody can do it, but we should do it when we're going to pick the site to drill a well, and not just jump out there and just drill because it's near a shade tree or something. So what about alluvial basin aquifers? That's where we have bedrock that doesn't make that much water, but it creates a basin that's full of sand. And so if we go to my part of the country, this is near Phoenix, Arizona. These gray areas are the mountains around the edge. And then this big basin here, it'd be like a fishbowl filled with sand, only in a huge scale. This is the west part of the city of Phoenix. So there's sand, silt, clay in there at different amounts and different locations. And if we look at this bedrock, we can just read the literature that's available in the public and understand some things about it. First of all, we consider where our rivers are. In this area, the river is drained by the Salt and Gila River, and then coming down to its New River and Alluvial, and that's what we show here. And we know from geological reports that these rivers have been there for a good long time, a few millennia. So they are what deposited the sediment that's there. And the USGS, fortunately for us, has gifted us with some mapping. So we know that these purple lines represent faults down towards the middle of the basin and stepping up towards the edges. And that orange shaded area, that's a salt body. We have a little salt dome in the west part of the Phoenix metropolitan area. So they've also, the USGS has also contoured this, so we can see the elevation contours of the top of bedrock. So we know that we get out, we have a shallow bedrock shelf, and it gets deeper and deeper as we go across these faults here, and the same over here, and so on and so forth. So this kind of gives us a definition of what our bowl is shaped like, a rock bowl, which is now filled with sand and silt and clay. So we know about the shape of the bowl, but we don't know about the sand and silt and gravel that's in it. Well, now we can look at well logs. And if we generalize, and let's say we have these three categories, sand and gravel, just sand, and clay, we can look where different categories of wells are. There's some in this area that have a whole lot of clay in the lower part, just a little bit of sand and gravel at the top. So we'll call those clay dominated. We see those here between this mountain, which happens to be called the White Tank Mountains, and this area. So this is probably where there was a big lake in many years past, which deposited that big clay layer. We have other wells which have a big clay in the middle, but coarse material above it and below it. We see that down this area close to where the Gila River exits the valley. And this is probably where there was stream sediments, and then it got backed up by some kind of a natural dam and made a big lake for a while. And then again, it broke that dam and now there's stream sediments again. So we have a situation like this all through this area. Then we have ones that alternate back and forth. This is where you have a stream that's meandering and moving around, switching from floodplain deposits to channel deposits. We see that both in the lower part, middle part of the valley and the upper middle part of the valley. So this makes sense. This is where the tributary streams that are going into these rivers would have been flowing the material into the valley. And then finally, we have the ones that we like the best, dominated by sand and gravel. Well, this is in the upper reaches, in the higher watershed of our valley. So we can see where these things are, and we see that they define zones. And so we're talking about a big, big area here, but we can at least categorize it as the clay dominated, or sand and gravel with middle clay layer dominated, clays with sand stringers, or sand and gravel dominated. This tells us generally what's going on with the wells, so we can at least, we may not be able to, depending on what properties that our client owns, we may not be able to go to the best areas. We might have to work within a more challenging area, but we can at least tell them what to expect. And the next steps, I'm not showing graphically here, but we need to consider things like environmentally sensitive areas, areas that might have a contaminant plume, or maybe endangered species, or other things like how far are we from a pipeline? How far are we from a water treatment plant? Things like that, land ownership, all these different non-hydrogeological considerations, but we layer them onto this stuff, and it can give us a good approach to picking the best possible well site. One last thing we need to consider, and then there's our salt dome. That kind of makes sense too. It's right by where our red lake deposits were. But one last thing we need to consider is well impacts. Now, maybe we're going to put in the well on the right, our new well here, but there may be an existing well nearby, and we may not have any regulatory concerns, but we also have to consider that when we pump our well and we cause a drawdown, that's shown in the yellow arrow there, then we also cause a little bit of a drawdown on our neighbor's well. And when they pump their well, they also cause a little drawdown on us, shown by that green arrow there. But when we pump both wells at the same time, those two drawdowns are additive. So it'd be more like the black line, not the yellow and not the green. And so we need to consider this for future operation of our well. How deep do we need to go? How much drawdown will it have? It might have a certain amount of drawdown that we test and determine when we first put it in, but later in time, if we run it and our neighbors run their wells at the same time, that may change. So that's what I'm saying. We need to consider well spacing from one another, as well as everything else when we consider our location for our well. So that's it on well siting. And in general, all these things are good starting points. But like I said earlier, you may want to move to other more sophisticated, even groundwater modeling level efforts. This is not uncommon, and it's worth it because the cost of the well these days are not trivial. So with that, I hope you do well out there, have successful and good work for the folks that need water, and stay safe.